In the early 19th century, the scientific understanding of nature was built almost entirely upon what could be directly observed, measured, or mechanically explained. Motion could be tracked, sound could be analyzed as vibrations, and light was treated largely as a visible phenomenon that traveled in straight lines or bent through lenses. Yet beneath this surface of apparent clarity existed a hidden layer of reality that puzzled even the greatest minds of the age. Electricity and magnetism were known to exist, but they behaved like ghosts of the physical world, powerful, undeniable, and yet invisible. Sparks jumped across gaps, compasses turned without touch, and currents flowed through wires without any obvious medium. Scientists could describe these effects individually, but they could not explain what truly connected them, or how they acted across empty space. Before Maxwell, electricity and magnetism were studied as separate subjects, each with its own laws, experiments, and limitations. Electricity was often associated with static charges, shocks, and later with currents flowing through conductors. Magnetism, on the other hand, was linked to lodestones, compass needles, and the Earth's magnetic field. These forces seemed mysterious because they acted at a distance. Unlike mechanical contact, where one object pushes another, electrical and magnetic forces appeared to reach through space itself. This idea deeply troubled scientists who were trained to think in terms of direct physical interaction. How could something act where nothing visible existed? The dominant scientific worldview of the time was strongly influenced by classical mechanics, especially the ideas of Isaac Newton. Newton's laws had explained the motion of planets, falling objects, and projectiles with remarkable success. Even gravity, though invisible, was treated as a force acting instantaneously across space. However, gravity was an exception that many scientists accepted reluctantly. When electricity and magnetism showed similar action at a distance, the discomfort grew stronger. There was a widespread desire to explain all forces through direct contact or mechanical models, often involving hypothetical particles or fluids that no one could see. As a result, early theories of electricity and magnetism were filled with imaginative but fragmented ideas. Some scientists proposed that electricity was a kind of fluid that flowed through materials. Others believed there were two separate electric fluids, positive and negative, whose imbalance caused electrical effects. Magnetism was sometimes explained using tiny magnetic particles or vortices inside matter. These models were useful for certain experiments, but they failed to provide a unified or deeply satisfying explanation. They described what happened, but not why it happened in a fundamental sense. Experiments continued to reveal surprising connections that challenged the separation of these forces. In 1820, Hans Christian Rasted discovered that an electric current could deflect a magnetic compass needle. This single observation shook the scientific world. It suggested that electricity and magnetism were not independent after all, but somehow linked. André-Marie Ampère quickly followed with mathematical descriptions of how electric currents produce magnetic effects. Michael Faraday later demonstrated that changing magnetic fields could induce electric currents. These discoveries hinted at a deeper unity, but the overall picture remained incomplete and confusing. Faraday, in particular, introduced a revolutionary way of thinking about invisible forces. Unlike many of his contemporaries, he was not primarily a mathematician. Instead, he relied on physical intuition and experimental insight. He proposed that electric and magnetic effects were not transmitted instantly across empty space, but through something he called fields. Faraday imagined space filled with lines of force that connected charges and magnets. These lines were not just abstract drawings. To Faraday, they represented a real physical structure in space. This idea was radical and controversial because it challenged the long-held belief that space itself was empty and passive. Despite the brilliance of Faraday's vision, many scientists struggled to accept it. Fields were invisible, intangible, and difficult to measure directly. Without a strong mathematical framework, Faraday's ideas remained qualitative rather than precise. As a result, the scientific community was divided. Some researchers continued to favor action at a distance theories, while others were intrigued by the possibility that space itself played an active role in transmitting forces. The invisible world was becoming more complex, not less. This was the state of science into which James Clerk Maxwell was born. The invisible world existed, but it was fragmented, poorly unified, and philosophically troubling. Scientists could manipulate electricity and magnetism in laboratories, but they lacked a single, coherent framework that explained how these forces truly operated. There was no clear answer to fundamental questions. What exactly is an electric current? How does a magnetic field exist in empty space? What medium carries these effects from one place to another? These questions lingered without resolution. Technology, meanwhile, was advancing rapidly. Telegraph wires stretched across continents, carrying electrical signals faster than any physical messenger. Engineers learned how to harness electrical power for practical use, even while scientists debated its true nature. This gap between practical success and theoretical understanding made the mystery even more striking. Humanity was using forces it did not fully comprehend. The invisible world was becoming increasingly important, yet it remained conceptually elusive. The lack of unification also limited scientific progress. Each new discovery added another piece to the puzzle, but without a guiding framework, the pieces did not easily fit together. Laws existed, but they were often empirical rules rather than deep principles. Electricity had its equations, magnetism had its own, and optics was treated as a separate domain altogether. Light, although known to be a wave by some and a particle by others, was not yet clearly linked to electricity or magnetism. Nature appeared divided into compartments, each governed by different rules. Philosophically, this fragmentation reflected a deeper uncertainty about the nature of reality itself. If forces could act invisibly across space, what did that say about the structure of the universe? Was space truly empty, or was it filled with something unseen? Did invisible forces have a physical existence, or were they merely mathematical conveniences? These questions were not just technical, they touched the foundations of how humans understood the world around them. It is important to recognize that before Maxwell, the invisible world was not ignored or dismissed. On the contrary, it was intensely studied, debated, and explored. But it lacked a unifying vision. Scientists stood at the edge of a hidden realm, aware of its power, but unable to map it fully. The invisible forces of electricity and magnetism were like scattered clues in a mystery without a solution. Each experiment revealed a new effect, yet the underlying story remained incomplete. This uncertainty created the perfect conditions for a transformative breakthrough. What was needed was not just another experiment or another isolated law, but a new way of seeing the invisible world as an interconnected whole. The stage was set for someone who could bridge experiment and theory, intuition and mathematics, visibility and invisibility. Before Maxwell's defining moment, the invisible world was a landscape of shadows, real, influential, and essential, yet lacking clarity and unity. It was a world waiting to be redefined. As the 19th century progressed, the tension between observation and explanation grew even sharper. Scientists were surrounded by evidence that invisible forces governed much of nature, yet their intellectual tools felt insufficient to fully grasp those forces. Laboratories produced sparks, currents, and magnetic effects with increasing reliability, but the underlying mechanisms remained hidden behind layers of assumption and approximation. This created a strange paradox. The more successful experiments became, the more obvious it was that the theoretical picture was incomplete. The invisible world was proving itself indispensable, yet it resisted being fully understood. One of the deepest problems lay in the concept of space itself. In classical thinking, space was considered an empty stage upon which physical events occurred. Objects moved through it, forces acted across it, but space itself played no active role. Electricity and magnetism challenged this assumption directly. If a charged object could influence another object without touching it, something had to be happening in the space between them. Yet no one could clearly define what that something was. Attempts to fill space with hypothetical substances, such as electrical fluids or mechanical ethers, multiplied, but none provided a completely convincing explanation. The idea of an ether, in particular, became a common attempt to solve the mystery. Many scientists believed that waves, by definition, required a medium to travel through. Since sound needed air and water waves needed water, it seemed logical that light and electromagnetic effects must also require a medium. This invisible ether was imagined as filling all of space, penetrating all matter, and transmitting forces and vibrations. However, the ether was never directly detected. Its properties had to be adjusted repeatedly to fit experimental results, making it feel more like a mathematical convenience than a physical reality. Still, without a better alternative, the ether remained a dominant assumption. At the same time, experimental discoveries continued to blur the boundaries between known phenomena. Faraday's work showed that electricity could be generated from magnetism and magnetism from electricity, depending on how conditions changed. This suggested that the two were not merely linked, but dynamically intertwined. The invisible world was no longer static, it was active, responsive, and capable of change over time. Forces were not just present, they evolved, spread, and interacted. This dynamic character demanded a new kind of explanation, one that went beyond fixed laws and isolated effects. Another challenge was the role of mathematics in understanding invisible phenomena. Many earlier scientists relied heavily on mechanical models, gears, springs, and particles colliding, to explain natural processes. These models worked well for visible motion, but struggled when applied to abstract forces. Mathematics offered a way to describe relationships without relying on physical pictures, but not everyone trusted it. Some viewed mathematical equations as mere tools for calculation rather than windows into reality. This skepticism slowed progress, as the invisible world increasingly required abstract thinking rather than concrete imagery. The scientific community itself was divided along these lines. Experimentalists emphasized measurement and observation, often avoiding deep theoretical claims. Theorists sought unifying principles but risked drifting too far from empirical evidence. Communication between these groups was not always smooth. Faraday's intuitive ideas about fields, for example, were admired for their creativity but criticized for their lack of mathematical rigor. As a result, his vision of space filled with lines of force remained incomplete, powerful in concept but fragile in acceptance. Education and tradition also played a role in maintaining the fragmented view of the invisible world. Physics textbooks treated electricity, magnetism, and optics as separate subjects, each with its own set of rules. Students learned formulas without being encouraged to see connections between them. This compartmentalization reinforced the idea that nature itself was divided rather than unified. It became difficult to imagine that light, a familiar visible phenomenon, could be fundamentally related to electrical sparks or magnetic fields. Beyond science, the broader cultural understanding of invisible forces was equally conflicted. Electricity was often seen as a mysterious power, almost magical in nature. Public demonstrations emphasized spectacle rather than explanation, reinforcing the sense that these forces were beyond ordinary comprehension. Magnetism was associated with navigation and curiosity, not deep physical theory. The invisible world inspired wonder, but also confusion and myth. This cultural backdrop made it even harder to establish a clear, rational framework for understanding unseen forces. Yet within this confusion lay a growing sense of anticipation. Many scientists felt that the existing theories were approaching their limits. Too many discoveries pointed toward a hidden unity for it to be ignored indefinitely. The invisible world seemed to be speaking in fragments, offering clues that demanded interpretation. There was a sense that a deeper order existed, waiting to be revealed by someone capable of seeing beyond the boundaries of established disciplines. This period can be understood as a moment of intellectual pressure. Ideas were accumulating faster than they could be organized. Each new experiment added weight to the argument that electricity and magnetism were aspects of a single phenomenon, but no one had yet found the language to express that unity fully. The invisible world was like a complex melody heard in pieces, recognizable but incomplete. Scientists knew there was harmony, but they could not yet write the full score. It is within this context that the significance of Maxwell's later achievement becomes clearer. Before his intervention, the invisible world was real but unstable in theory. It existed as a collection of effects rather than a coherent system. Space was still mostly passive, forces were still mysterious, and light remained disconnected from electromagnetism. The scientific imagination was stretched to its limits, struggling to move beyond action at a distance and mechanical analogies. The importance of this pre-Maxwell era lies not in its failures, but in its readiness for transformation. The questions were clear, the evidence was abundant, and the need for unification was undeniable. What was missing was a mind capable of embracing abstraction without losing contact with reality, a thinker who could treat mathematics not just as a tool, but as a language of nature itself. The invisible world, though poorly understood, had reached a point where it could no longer remain fragmented. Thus, before Maxwell's defining moment, the scientific world stood at a threshold. Invisible forces had moved from curiosity to central importance. They powered technology, challenged philosophy, and reshaped scientific debate, yet they lacked a clear identity. They were known by their effects, not by their essence. The stage was fully set for a revolutionary insight, one that would turn invisibility into structure, mystery into law, and scattered phenomena into a unified vision of reality. When James Clerk Maxwell began his work, electricity and magnetism were already known to be related, but that relationship was incomplete, fragile, and deeply confusing. Experiments had shown links between electric currents and magnetic effects, and between changing magnetic fields and induced currents, yet these connections appeared more like clever tricks of nature than expressions of a single underlying truth. What Maxwell achieved was not merely the addition of another discovery to this growing list, but the creation of a unified vision in which electricity, magnetism, and light became different faces of the same invisible reality. Maxwell approached the problem with a rare combination of deep respect for experimental results and extraordinary mathematical imagination. He studied the work of Faraday closely, especially the idea that space itself was filled with fields rather than being an empty void across which forces mysteriously jumped. Where Faraday drew lines of force to visualize invisible interactions, Maxwell sought a precise language that could describe those interactions without ambiguity. He believed that mathematics could do more than calculate outcomes. It could reveal structure, symmetry, and meaning hidden beneath appearances. At the time, the laws of electricity and magnetism existed as separate mathematical statements. Coulomb's law described the force between electric charges. Ampere's law explained how electric currents produced magnetic fields. Faraday's law showed how changing magnetic fields generated electric currents. Each law worked within its own domain, but there was no single framework that bound them together. Maxwell's genius lay in seeing these laws not as isolated rules, but as pieces of a larger pattern waiting to be assembled. One of Maxwell's most important insights was recognizing that changing electric fields must also produce magnetic effects, even in empty space. This idea was not obvious and had no direct experimental proof at the time. Yet Maxwell realized that without this missing piece, the symmetry between electricity and magnetism remained incomplete. By introducing what he called the displacement current, Maxwell extended Ampere's law in a way that preserved consistency across all situations. This single conceptual step transformed the theory from a patchwork of rules into a balanced and self-contained system. With this addition, Maxwell's equations emerged as a unified description of electromagnetic phenomena. These equations showed that electric fields and magnetic fields are not independent entities, but continuously generate and influence each other. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This mutual interaction means that electromagnetic effects can propagate through space without the need for wires, charges, or magnets as carriers. The invisible world was no longer static or localized, it was dynamic and self-sustaining. From this unified framework came one of the most profound revelations in the history of science. When Maxwell analyzed his equations, he discovered that they predicted the existence of waves traveling through space at a specific speed. When he calculated that speed using known electrical and magnetic constants, the result matched the measured speed of light. This was not a coincidence or a convenient approximation. It was a precise numerical agreement that demanded interpretation. Maxwell concluded that light itself is an electromagnetic wave. This conclusion was revolutionary because it united three previously separate domains of physics. Electricity, magnetism, and optics were no longer distinct subjects governed by unrelated principles. Light, which had been studied for centuries as a visible phenomenon, was revealed to be a manifestation of the same invisible fields responsible for electrical sparks and magnetic attraction. The visible world and the invisible world were suddenly part of a single continuum. What humans could see with their eyes was only a narrow slice of a much broader electromagnetic spectrum. The unification achieved by Maxwell did more than explain known phenomena, it predicted entirely new ones. If light was an electromagnetic wave, then there was no reason to believe that all such waves were visible. Maxwell's theory implied the existence of electromagnetic radiation with wavelengths longer and shorter than visible light. These waves would be invisible to the human eye, yet physically real. Decades later, radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays were discovered, each confirming Maxwell's vision with astonishing precision. What made Maxwell's unification especially powerful was its abstraction. He did not rely on mechanical models or hypothetical particles moving through space. Instead, he described reality in terms of fields and their relationships. This shift marked a turning point in physics. Fields became fundamental entities, not just mathematical conveniences. Space itself acquired physical properties capable of storing energy and transmitting influence. The invisible world gained structure and legitimacy as a real component of nature. Despite its elegance, Maxwell's unification was not immediately embraced. Many scientists found his equations difficult and his conclusions unsettling. The idea that light was an electromagnetic wave challenged long-standing debates about whether light was composed of particles or waves. The concept of fields acting independently of matter seemed too abstract for those accustomed to mechanical explanations. Maxwell's work demanded a new way of thinking, one that valued mathematical consistency as much as experimental intuition. Yet the strength of Maxwell's unification lay precisely in this consistency. His equations did not merely fit existing data. They held together logically, with each part supporting the others. They explained why electric and magnetic phenomena behaved as they did and why their interactions followed specific patterns. More importantly, they reduced complexity by showing that diverse effects arose from simple, unified principles. Nature, once fragmented, appeared coherent and ordered. The unification of electricity, magnetism, and light also changed the goals of physics itself. It demonstrated that seemingly unrelated phenomena could share a common foundation, encouraging scientists to search for deeper unities elsewhere. This mindset would later inspire efforts to unify space and time, mass and energy, and eventually the fundamental forces of nature. Maxwell's achievement became a model for what theoretical physics could accomplish when guided by insight and rigor. In practical terms, this unification laid the groundwork for modern technology. Although Maxwell himself did not design radios or communication systems, his equations made them possible. Once electromagnetic waves were understood as real and controllable, engineers learned to generate, transmit, and detect them. The invisible world described by Maxwell became a medium for information, connecting people across vast distances without physical contact. This transformation of daily life stands as one of the clearest demonstrations of the power of theoretical unification. At its core, Maxwell's unification was a philosophical achievement as much as a scientific one. It challenged the assumption that reality must always be directly observable to be real. It showed that invisible structures could be more fundamental than visible objects. Electricity and magnetism were no longer mysterious forces acting at a distance. They were expressions of continuous fields woven into the fabric of space itself. This was the moment when the invisible world ceased to be a collection of isolated curiosities and became a unified domain governed by universal laws. Maxwell did not merely connect existing ideas, he transformed the way humans understood nature. By revealing the deep unity between electricity, magnetism, and light, he reshaped physics into a discipline capable of seeing beyond appearances, uncovering order where only mystery had existed before. As Maxwell's unified vision began to take shape, its deeper implications slowly unfolded, extending far beyond the immediate connection between electricity, magnetism, and light. What he had created was not simply a theory that linked known phenomena, but a new way of describing reality itself. His equations suggested that the universe was not governed solely by forces acting between objects, but by continuous fields that existed everywhere, even in the apparent emptiness of space. This idea quietly redefined what physicists meant by nothingness, transforming empty space into an active participant in physical processes. One of the most profound consequences of Maxwell's unification was the realization that electromagnetic phenomena did not require matter to exist or propagate. Electric and magnetic fields could sustain one another and travel through space independently. This was a radical departure from earlier thinking, which assumed that all physical effects required some material carrier. Maxwell's equations showed that fields could store energy, transfer momentum, and evolve over time on their own. The invisible world was no longer secondary to matter, it became fundamental. This shift had a deep conceptual impact on how scientists understood causality. In classical mechanics, causes and effects were often direct and localized. One object pushed another, and motion followed. In Maxwell's framework, causes could be distributed across space and time. A change in one region of space could influence another region through the propagation of a field, not instantaneously, but at a finite speed. This introduced a new sense of order and limitation into nature. Information and influence could not travel infinitely fast, they were constrained by the speed of electromagnetic waves, later recognized as a universal speed limit. The unification also reshaped the relationship between theory and experiment. Maxwell's prediction of electromagnetic waves was a triumph of pure reasoning. At the time, no one had observed such waves directly, yet the mathematics demanded their existence. This marked a turning point in science, demonstrating that equations could reveal aspects of reality before experiments confirmed them. When Heinrich Hertz later detected radio waves in the laboratory, it was not merely a new discovery, it was a validation of Maxwell's vision and of theoretical physics as a powerful tool for uncovering truth. As electromagnetic theory matured, it began to influence other areas of physics. The field concept spread beyond electricity and magnetism, shaping how scientists thought about gravity, fluids, and even quantum phenomena. Fields became a central element of modern physics, replacing older mechanical pictures that relied on particles alone. Maxwell's work helped establish the idea that nature could be described by continuous structures governed by differential equations, an approach that would dominate scientific thinking for generations. The unification of electricity and magnetism also brought a new sense of elegance and simplicity to physics. Where there had once been a collection of unrelated laws, there was now a compact set of equations capable of explaining a vast range of phenomena. This economy of description suggested that nature itself was built on simple principles, even if their consequences were complex. Such elegance was not merely aesthetic, It provided confidence that the theory reflected something deeply real about the structure of the universe. Culturally and intellectually, Maxwell's achievement changed how invisibility was perceived. Invisible forces were no longer associated with mystery or superstition, but with precise laws and predictable behavior. The unseen became trustworthy, measurable, and intellectually respectable. This shift helped bridge the gap between common sense and scientific abstraction. Even though people could not see electromagnetic fields, they could understand them as real entities with clear properties and effects. The unification also altered the trajectory of technological development. Once electromagnetic waves were understood as natural consequences of changing fields, engineers could deliberately create and manipulate them. Communication technologies emerged directly from this insight, turning the invisible world into a practical medium for human connection. Signals traveling through space became extensions of Maxwell's equations in action. What began as abstract theory evolved into infrastructure that reshaped society. Perhaps most importantly, Maxwell's work laid the intellectual foundation for later revolutions in physics. Albert Einstein's theory of special relativity was deeply influenced by the structure of Maxwell's equations, particularly their insistence on a constant speed of light. Einstein recognized that the laws of electromagnetism did not fit comfortably within the older notions of absolute space and time. By taking Maxwell's unification seriously, he was led to rethink the nature of time, space, and simultaneity. In this sense, Maxwell's moment did not end with electromagnetism, it echoed into the very fabric of modern physics. The unification also revealed a subtle philosophical lesson about human knowledge. It showed that reality does not always present itself in easily separable categories. Electricity, magnetism, and light appeared different to the senses, yet they were expressions of the same underlying structure. This challenged the tendency to classify phenomena based solely on appearance. Maxwell demonstrated that true understanding often lies beneath the surface, accessible only through careful reasoning and abstraction. There was also a humbling aspect to this achievement. Maxwell himself did not fully grasp all the consequences of his equations, nor did he witness many of their confirmations. His work illustrated how scientific progress often transcends individual lifetimes. Ideas can be more powerful than their creators, unfolding gradually as future generations explore their implications. The invisible world he revealed continued to expand long after his death. Over time, Maxwell's unification became so deeply integrated into physics that it began to feel almost inevitable. Yet this sense of inevitability is misleading. It required extraordinary imagination to see unity where others saw fragmentation, and courage to trust mathematics when direct evidence was lacking. Maxwell's achievement reminds us that major advances in understanding often arise from rethinking familiar facts in a radically new way. In the broader history of science, the unification of electricity, magnetism, and light stands as one of the greatest syntheses ever achieved. It transformed invisible forces into a coherent system, elevated fields to fundamental status, and revealed light as a bridge between the seen and unseen. This unification did not close the book on physics. Instead, it opened new chapters filled with deeper questions and richer possibilities. By the time Maxwell's ideas were fully accepted, the invisible world had been permanently redefined. It was no longer a realm of isolated effects and puzzling actions at a distance. It became an ordered domain governed by universal laws capable of explanation, prediction, and technological application. Through this unification, Maxwell showed that the hidden structures of nature are not beyond human understanding, but accessible to those willing to look beyond appearances and trust in the power of reason. Maxwell's extraordinary achievement in unifying electricity and magnetism relied not only on his insight into the physical world, but also on his remarkable ability to translate intuition into precise mathematics. Long before many physicists of his time fully appreciated the power of abstract reasoning, Maxwell recognized that mathematics was not merely a tool for calculation, It was a language capable of revealing hidden structures in nature. His approach combined the rigor of mathematical logic with the creativity of physical intuition, producing a framework that could describe phenomena invisible to the senses with astonishing clarity. This capacity to see through equations transformed the study of physics, setting a precedent for generations of scientists to follow. Mathematics, in Maxwell's hands, was more than a symbolic system. It became a lens through which the invisible world could be observed, understood, and predicted. The challenges he faced were immense. Prior to Maxwell, electricity and magnetism were treated largely through separate experimental laws. Coulomb's law described the forces between electric charges. Ampere's law captured how electric currents generate magnetic effects. Faraday's experiments revealed how changing magnetic fields could induce electric currents. Each of these laws worked in its own domain, but none provided a complete picture of the underlying reality. Maxwell's genius lay in recognizing that these disparate results were manifestations of a deeper unity, and that mathematics could articulate that unity in a concise and coherent form. Maxwell approached the problem with extraordinary conceptual boldness. He did not merely rearrange existing equations, he introduced new mathematical constructs to capture phenomena that had previously resisted formal description. One of the most famous of these was the displacement current, a term he added to Ampere's law to account for the behavior of electric fields in situations where no physical current was present. This extension was not suggested by experiment alone, it arose from a commitment to mathematical consistency. Maxwell realized that without this term, the equations describing electric and magnetic fields would be incomplete, unable to account for the dynamic interplay between them. By including the displacement current, he ensured that the laws governing the invisible world were symmetrical and self-consistent. This mathematical insight allowed Maxwell to see patterns that were invisible in the laboratory. While Faraday had intuitively described lines of force and field interactions, he lacked the quantitative language to make precise predictions. Maxwell's equations translated Faraday's qualitative observations into a formal system that could predict outcomes in any conceivable configuration of charges and currents. In doing so, Maxwell transformed the invisible world from a collection of isolated effects into a structured, predictable domain. Fields could be calculated, waves could be described, and interactions could be anticipated with unprecedented accuracy. The use of mathematics as a descriptive tool also allowed Maxwell to transcend the limitations of human senses. Electric and magnetic fields are inherently invisible. They cannot be seen, touched, or directly measured without instrumentation. By expressing these fields through equations, Maxwell gave scientists a way to understand their behavior even when it could not be observed directly. He provided a bridge between intuition and empirical evidence, enabling predictions about phenomena that would only be confirmed decades later. This abstract approach elevated the role of mathematics in physics, demonstrating that true understanding often requires thinking beyond the immediately observable. Moreover, Maxwell's mathematical framework revealed the underlying symmetry of nature in a way that was both elegant and profound. His equations showed that electric and magnetic fields are intimately connected, continuously generating and influencing each other. A changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. This mutual interdependence forms the foundation of electromagnetic waves, which propagate through space at a finite speed. The elegance of the mathematics mirrored the elegance of nature itself, suggesting that simplicity and beauty are often clues to deep truth. Maxwell's approach also had a predictive power that set it apart from previous methods. Before his work, scientists could describe individual experiments, but they lacked a framework that could anticipate new phenomena. By treating fields mathematically, Maxwell discovered that his equations implied the existence of electromagnetic waves traveling at the speed of light. This prediction was entirely theoretical. No one had yet observed such waves in the laboratory. The mathematics itself, independent of direct experimental proof, revealed a new domain of reality. When Heinrich Hertz later confirmed the existence of radio waves, it was a powerful validation of Maxwell's vision and the power of mathematical reasoning. The precision of Maxwell's equations also allowed for practical applications long before the underlying phenomena were fully exploited technologically. Engineers could design circuits, antennas, and communication devices using principles derived directly from Maxwell's formalism. The equations provided exact relationships between electric and magnetic quantities, ensuring that designs could function reliably even when the behavior of invisible fields might otherwise seem mysterious. In this way, Maxwell's mathematical insight bridged the gap between abstract theory and real-world application, demonstrating the practical utility of rigorous reasoning. Maxwell's use of mathematics also fostered a new philosophical perspective on the invisible world. By demonstrating that unseen forces could be captured entirely within a logical, consistent framework, he challenged the prevailing assumption that reality had to be directly observable to be meaningful. Invisible entities, fields, waves, and forces gained legitimacy and explanatory power. Mathematics became a tool not just for calculation, but for understanding, prediction, and discovery. The invisible world was no longer mysterious or magical, it was intelligible, governed by universal principles that could be explored systematically. The abstraction inherent in Maxwell's approach also prepared the ground for future advances in physics. By showing that fields could exist and interact independently of matter, he set the stage for later theories in relativity and quantum mechanics. His work demonstrated that reality could be described by continuous structures and differential equations, rather than solely by particles or mechanical interactions. Fields became fundamental entities, capable of carrying energy, momentum, and information across space. This conceptual shift opened new avenues of thought, transforming the study of nature at the most fundamental level. Furthermore, Maxwell's mathematical vision revealed a unity in nature that had previously been hidden. By describing electric and magnetic phenomena as aspects of a single system, he provided a coherent picture in which the visible and invisible were interconnected. Light, an experience of the senses, was shown to be an electromagnetic phenomenon, a manifestation of the same fields responsible for sparks and currents. The mathematics did not merely describe the world, it illuminated the profound connections that underlay appearances, showing that the invisible structures of nature are as real and consequential as what we can see and touch. This ability to unify theory, predict new phenomena, and translate intuition into rigorous formalism makes Maxwell's use of mathematics one of the most significant achievements in the history of science. It demonstrates how abstract reasoning can uncover hidden truths, turning the invisible world from a realm of uncertainty into a domain of precise, comprehensible structure. Maxwell's equations did more than explain known effects, they opened an entirely new way of seeing, thinking, and understanding the fundamental forces that shape the universe. By combining intuition with formal reasoning, Maxwell transformed mathematics into a lens that could reveal the invisible, making the unseen tangible through logic and prediction. This insight not only allowed him to unify electricity, magnetism, and light, but also changed the very methodology of physics, setting a precedent for all subsequent work in theoretical and applied science. Maxwell's ability to translate physical intuition into mathematics had consequences that extended far beyond the immediate unification of electricity, magnetism, and light. By creating a precise formalism, he opened the door to predicting phenomena that had never been observed, demonstrating that mathematics could reveal hidden truths about nature before experiments confirmed them. This approach marked a fundamental shift in how science approached the invisible world. No longer was the role of theory confined to describing what could already be measured. Instead, theory itself became a tool for discovery, capable of guiding experimental inquiry and shaping the trajectory of technological innovation. One of the most striking outcomes of Maxwell's mathematical insight was the prediction of electromagnetic waves. His equations implied that oscillating electric and magnetic fields would generate self-propagating disturbances that travel through space at a constant speed. This was a radical conclusion because it extended the reach of electromagnetic phenomena far beyond what had been experimentally demonstrated. While laboratory experiments had revealed that electric currents could induce magnetic effects and vice versa, the idea that these interactions could produce waves moving through empty space was entirely new. The mathematics made a bold claim about the structure of reality. The invisible world was dynamic, capable of sustaining energy and information across vast distances. The precise nature of Maxwell's equations also provided a new framework for understanding the relationship between visible and invisible phenomena. By showing that light itself was an electromagnetic wave, he connected the human sensory experience with the underlying invisible forces. The mathematics revealed that what we perceive as color, brightness, or intensity is merely a particular manifestation of broader electromagnetic processes. This insight dissolved the artificial boundaries between different domains of physics, showing that the visible world is inseparable from the invisible fields that permeate space. The predictive power of the equations highlighted that mathematics could uncover unity where the senses and experiments alone might suggest fragmentation. Maxwell's approach also reshaped the experimental strategies of future scientists. By demonstrating that invisible structures could be mathematically modeled, he provided a template for designing experiments aimed at confirming theoretical predictions. Heinrich Hertz's later discovery of radio waves exemplifies this process. Guided by Maxwell's formalism, he was able to detect electromagnetic waves that had previously been only a theoretical prediction. This interplay between theory and experiment emphasized that mathematics was not merely descriptive, but generative. It could point toward new realities, direct observation, and validate understanding in ways that purely empirical approaches could not. Another consequence of Maxwell's mathematical methodology was the elevation of abstraction in physics. The invisible world could no longer be fully captured by mechanical analogies or tangible models. Fields, lines of force, and waves became central concepts, existing independently of matter yet interacting with it in predictable ways. By formalizing these concepts mathematically, Maxwell legitimized a mode of thinking that valued logical consistency and symmetry as indicators of truth. The invisible forces governing the universe were shown to be accessible not through direct perception, but through reasoning and calculation, expanding the tools available to scientists for exploring reality. Maxwell's equations also revealed the deep symmetry inherent in nature, a symmetry that would become a guiding principle for later developments in physics. The equations treat electric and magnetic fields as dual aspects of a single entity, interacting in a self-consistent, continuous manner. This symmetry suggested that the universe is organized according to simple, harmonious principles, even when phenomena appear complex and disconnected. Mathematics, in this context, serves as a key to deciphering the underlying order, turning the invisible into a comprehensible and structured domain. The influence of Maxwell's mathematical insight extended to technological and practical applications as well. Once the behavior of electromagnetic fields was understood quantitatively, it became possible to design systems that manipulate these fields with precision. Radio transmitters, electrical circuits, and later communication networks were all predicated on the ability to calculate, predict, and control electromagnetic behavior. The invisible world became a medium through which humans could transmit energy and information, all guided by the theoretical framework Maxwell had provided. His mathematics bridged the gap between conceptual understanding and practical application, demonstrating the tangible value of abstract reasoning. Philosophically, Maxwell's work also challenged conventional notions of reality and observation. He showed that entities that cannot be directly seen or touched, fields, waves, and energy, can have real measurable effects and obey exact laws. This insight shifted the scientific understanding of what counts as real, expanding it to include invisible structures that nonetheless govern the behavior of the material world. Mathematics became a tool for validating existence in ways that sensory perception alone could not provide. Finally, Maxwell's success in using mathematics to describe the invisible world inspired a new generation of scientists to adopt similar approaches. The methodology of combining physical intuition with formal reasoning became a hallmark of modern physics, influencing fields as diverse as quantum mechanics, relativity, and cosmology. The invisible world could be explored systematically, predicted accurately, and incorporated into a coherent understanding of nature, all thanks to Maxwell's vision and mathematical ingenuity. In sum, Maxwell's ability to see the unseen through mathematics transformed physics. It revealed hidden structures, connected previously isolated phenomena, and expanded the very concept of scientific explanation. By showing that invisible forces could be formalized, predicted, and ultimately harnessed, Maxwell established a new paradigm in which the language of mathematics became inseparable from the pursuit of understanding the natural world. His work demonstrated that the invisible world, though intangible, is no less real, no less ordered, and no less capable of influencing human knowledge and technology than the visible world around us. Maxwell's revolutionary work revealed the existence of electromagnetic waves, a concept that fundamentally changed humanity's understanding of the invisible world. Prior to Maxwell, electricity and magnetism were treated largely as separate forces, with experiments showing isolated effects but no clear mechanism for how they interacted across space. Maxwell's equations demonstrated that changing electric and magnetic fields are interdependent and can sustain one another, producing waves that travel through empty space. This was an extraordinary insight, as it showed that invisible forces could propagate without any physical medium, carrying energy and information across vast distances. The concept of electromagnetic waves unified several areas of physics that had previously seemed disconnected. Light, which had been studied for centuries as a visual phenomenon, was revealed to be a form of electromagnetic radiation. By calculating the speed of these waves using known constants, Maxwell found a striking agreement with the measured speed of light. This discovery indicated that visible light, invisible radio waves, and other forms of electromagnetic radiation are all manifestations of the same underlying phenomenon. The invisible world, therefore, was not a series of isolated effects, but a continuum that included both the seen and unseen. Maxwell's prediction of electromagnetic waves also laid the foundation for modern communication and technology. Radio, television, radar, and wireless networks all rely on the principles he described. While Maxwell himself did not build these devices, his equations provided the theoretical framework that engineers later used to generate, transmit, and detect electromagnetic waves. The practical applications of these waves demonstrate how understanding invisible phenomena can directly transform human life. The idea that energy can travel invisibly across space was no longer theoretical. It became a tool for shaping the modern world. The existence of electromagnetic waves also inspired further scientific exploration. Experiments by Heinrich Hertz in the late 19th century confirmed Maxwell's predictions, providing experimental proof of a previously unseen reality. This interplay between theory and observation reinforced the power of Maxwell's equations and the importance of using mathematics to explore phenomena beyond direct sensory perception. The recognition that waves could exist unseen yet have measurable effects marked a turning point in physics, showing that the invisible world is structured, predictable, and accessible to human understanding. Maxwell's work demonstrated that what is invisible is not necessarily mysterious or unknowable. Electromagnetic waves carry energy, interact with matter, and can be calculated and harnessed. By revealing their existence, Maxwell bridged the gap between abstract theory and observable phenomena, transforming the study of light, electricity, and magnetism. His insight laid the groundwork for technologies and scientific advances that continue to shape the world today, illustrating the profound power of uncovering the structures hidden within the invisible world. Despite the brilliance of Maxwell's equations and their revolutionary implications, his ideas were not immediately or universally accepted. The scientific community of the 19th century was cautious, and many contemporaries found his work abstract, mathematically complex, and difficult to reconcile with established physical intuition. While laboratory experiments had long demonstrated electrical and magnetic phenomena, the idea that these effects could propagate as invisible waves through empty space challenged conventional understanding. Scientists were accustomed to thinking in terms of direct contact or mechanical action, and the notion of fields acting independently of matter seemed counterintuitive. Maxwell himself recognized the abstract nature of his work. He relied heavily on mathematical reasoning to reveal relationships that had not yet been fully confirmed experimentally. Concepts such as the displacement current and self-sustaining electromagnetic waves were novel and, at the time, purely theoretical. The mathematics indicated a coherent and unified system, yet many questioned whether it corresponded to physical reality. For some, the invisibility of the phenomena made them seem speculative, even fantastical. The equations predicted behavior that could not immediately be observed, which caused hesitation among scientists accustomed to empirical validation. Another factor contributing to delayed recognition was the complexity of Maxwell's equations themselves. They required a level of mathematical sophistication that exceeded the training of many experimentalists. While the underlying principles were simple in concept, expressing them formally demanded skill in differential calculus and vector analysis. This barrier limited the immediate dissemination and understanding of his ideas. Only a small group of mathematically trained physicists could fully appreciate the elegance and predictive power of his framework, which slowed widespread acceptance in the broader scientific community. Furthermore, the practical demonstration of Maxwell's predictions lagged behind the theory. The existence of electromagnetic waves had to be confirmed experimentally, and the tools to detect and measure them were not yet available. Heinrich Hertz's experiments decades later provided crucial verification, but until then, Maxwell's work remained largely theoretical. This delay reinforced skepticism among some scientists, as theory without immediate experimental evidence was often treated cautiously. The combination of abstract mathematics and unverified predictions contributed to a perception that Maxwell's ideas were ahead of their time. Despite these challenges, Maxwell's vision gradually gained recognition because of its internal consistency, explanatory power, and eventual experimental confirmation. Once Hertz demonstrated the existence of radio waves, the scientific community began to appreciate the accuracy and foresight of Maxwell's equations. What had once seemed abstract and intangible was validated as a precise description of reality. Over time, his work became foundational, influencing not only electromagnetism, but also the development of modern physics, including Einstein's theory of relativity. The initial resistance to Maxwell's ideas highlights how groundbreaking discoveries often face skepticism, particularly when they reveal an invisible world that challenges prevailing assumptions. Maxwell's groundbreaking work laid the foundation for future scientific revolutions, profoundly influencing Albert Einstein and the development of modern physics. The unification of electricity, magnetism, and light demonstrated that seemingly distinct phenomena could be understood as different expressions of a single underlying principle. This insight inspired Einstein to rethink the very nature of space, time, and motion. Maxwell's equations, which describe electromagnetic waves propagating at a fixed speed, implied that the speed of light is constant in all frames of reference. This concept directly challenged the Newtonian notions of absolute space and time that had dominated physics for centuries. Einstein recognized that Maxwell's work demanded a radical reevaluation of how motion and observation are related. If light always travels at the same speed, regardless of the observer's motion, then the classical understanding of time as uniform and absolute could no longer hold. This realization became one of the cornerstones of Einstein's special theory of relativity. By building upon Maxwell's equations, Einstein was able to develop a framework in which space and time are interwoven into a single continuum, and the laws of physics remain consistent for all observers. Maxwell's invisible fields thus indirectly reshaped our understanding of reality itself. Beyond relativity, Maxwell's influence extended into quantum theory and the study of the fundamental forces of nature. The concept of fields, formalized mathematically by Maxwell, provided a template for thinking about forces that act over a distance, a notion that would later be critical in understanding atomic and subatomic interactions. Quantum electrodynamics, the theory that describes the interaction of light and matter at the quantum level, can trace its conceptual lineage directly to Maxwell's insight that electromagnetic phenomena are continuous fields with measurable properties. In this way, his work became a bridge between classical physics and the revolutionary ideas of the 20th century. Maxwell's influence also reshaped experimental physics. By providing a clear theoretical framework, he guided future scientists in designing experiments that could test the predictions of his equations. Heinrich Hertz's verification of radio waves exemplifies this synergy between theory and observation. Maxwell's work showed that mathematical predictions could lead to discoveries of phenomena previously unknown, emphasizing that theoretical physics is not merely descriptive but predictive. This approach continues to define how physicists explore the invisible world today. The broader impact of Maxwell's insight is evident in technology as well. His unification of electromagnetic theory underpins nearly all modern electrical and communication technologies, from radio and television to wireless internet and satellite systems. Beyond practical applications, Maxwell's work influenced how scientists conceptualize the universe, teaching that unity and order can exist beneath apparent complexity. By shaping Einstein's theories and inspiring subsequent advances, Maxwell's vision of the invisible world became a cornerstone for understanding both the physical universe and the principles that govern it. Ultimately, Maxwell's contributions demonstrate that theoretical insights can have consequences far beyond their initial scope. By uniting electricity, magnetism, and light, he not only solved immediate scientific puzzles, but also laid the groundwork for the revolutionary transformations of the 20th century. His influence on Einstein and modern physics exemplifies how one profound understanding of the invisible world can redefine humanity's conception of reality itself, bridging the gap between observation, theory, and the deepest truths of nature. Maxwell's insights into the invisible world left an enduring legacy, not only in theoretical physics but also in practical technology and human understanding. By unifying electricity, magnetism, and light, he provided a framework that allowed humanity to manipulate and harness forces that had previously been mysterious and inaccessible. The practical implications of his work are immense, forming the foundation of modern communications, energy transmission, and countless devices that define contemporary life. Radio waves, television signals, radar systems, and mobile communications all operate according to principles first revealed by Maxwell's equations, demonstrating that understanding the invisible can directly transform society. The applications of Maxwell's theories extend far beyond communications. Electrical power generation and distribution rely on electromagnetic principles to convert mechanical energy into electricity, and to transport it efficiently across vast distances. Medical technologies, such as MRI machines, use electromagnetic fields to create detailed images of the body's interior, highlighting the power of invisible forces to provide insight into otherwise hidden structures. Even emerging fields like wireless energy transfer and advanced sensor technologies draw upon the understanding of electromagnetic fields that Maxwell formalized over a century ago. The invisible world he described is thus not only a subject of academic inquiry, but a practical resource that underpins modern civilization. Beyond technology, Maxwell's work profoundly influenced the way humans think about nature and knowledge. His equations showed that invisible forces are not chaotic or random, but governed by precise laws that can be understood, predicted, and applied. This challenged previous notions that reality was confined to what could be directly observed or mechanically manipulated. By revealing the structured behavior of forces beyond human perception, Maxwell expanded the scope of science itself, demonstrating that the universe contains layers of order that are accessible through reasoning, mathematics, and careful experimentation. Maxwell's legacy also lies in the inspiration he provided for subsequent scientific revolutions. His equations influenced not only Einstein's theories of relativity, but also the development of quantum mechanics and field theory, shaping modern physics in profound ways. The concept of fields as fundamental entities, capable of carrying energy and information, became central to understanding the forces that govern particles, atoms, and even the cosmos. Maxwell's unification encouraged a vision of nature in which complexity arises from simple underlying principles, guiding generations of scientists to seek deeper connections between seemingly disparate phenomena. Finally, Maxwell's work exemplifies the enduring power of human curiosity and intellect. He took phenomena that were invisible, misunderstood, and fragmented, and revealed their unity and elegance. By bridging theory and observation, mathematics and physical reality, he transformed abstract ideas into concrete understanding. The invisible world he uncovered is no longer mysterious, it is a foundation upon which modern science and technology are built. His insights continue to influence research, innovation, and our perception of the universe, proving that the discovery of unseen forces can redefine both science and the human experience. In essence, Maxwell's contributions created a bridge between the invisible and the tangible, showing that understanding hidden structures of nature can have profound consequences for knowledge, technology, and society. His legacy endures in every device that uses electricity, every signal transmitted invisibly through space, and every scientific endeavor that seeks to uncover the hidden principles governing the universe. Through Maxwell, the invisible world became not only comprehensible but indispensable, shaping the modern age in ways that continue to resonate today.